chunk of time and one person in it. So if you messed up even just a little bit, you'd still get the right answer. And so it's really obvious. Yeah, it was like between 1 and 3, and between like 1:45 and 2:15, like one person, and there's like every like 6 minutes.
She just like gives you like 90% for no reason. So like your grade is always
no one was
teetering
checking
on
in.
the A
So
to
if you mess up,
B.
All right, so we're going to talk about variation of parameters with systems. So very similar to what we did with variation of parameters for higher order differential equations. We're going to ask ourselves, can we come up with a solution that is some function times one of our known solutions? And if we can come up with a solution, what form does it have to take? Well, we need some preliminaries first. So we're going to say if we have a fundamental set of solutions.
real quick, Mr. Beamer.
Yeah?
You can't see anything.
Oh, yeah, you have to be able to see.
Oh, I wanted to see how long it would go.
You would have gone like 10 minutes.
No, surely like 2 minutes in you're like, oh wait. It's not done.
Yeah, sorry, I'm ruining it.
Yeah, like it wasn't been that.
Sorry, I'm a narc, guys. Not trying.
I was standing here thinking it's really cloudy today. It seems kind of dark. Wasn't going. All right, so we have a fundamental set of solutions. x1, x2, up through x sub n for our n by n system. And this is our fundamental solutions of x prime equals a times x. And this is on some interval. The general solution then we usually write x equals c1 x1 plus c2 x2 plus c sub n x sub n. And if we wrote out our matrices, we'd say x equals c1, and x1 is x11, x21 up to xn1. So we get column vectors for each of these, plus c2 times x21, x22 up to xn2. And we go up to however many solutions we have. This is going to be x1n up to xnn. Now we're going to rewrite this in a slightly different form. I'm just going to add all of these column vectors together and write one big matrix. So this would be c1 x11 plus c2 x21 plus up to cn x1n, and I'm just going to go all the way down to the last row here. C1 xn1 plus over to cn xnn. And we're going to write that just as one big column matrix with these all added together as each of our rows. Yes?
Is the last, is the term in the upper, right, 1n or n1?
1n.
No, down.
I don't know why he moves the
Why would it be 2, 1?
This should be, sorry, this should be n1, you're right.
In the big matrix.
There we go. And this should be, I think this should be 1n. 1n. That should be 1. First row, no, this should be 2, 1. And this is the row n1, yeah. And this is first row, nth column. So this should be 1, 2, first row. There we go. This should be 1, 2. Yeah. and that should be a 1n. There we go. So we write this as one big column matrix with all of those added together. And we can further simplify to, I'm going to say x equals, I'm going to write a new matrix, phi of t, this is capital Phi, times c, where c is the matrix of the constants, C1, C2, up to Cn, and phi of t is just the matrix of all of the individual solution functions. So that's x11, x12, x1n, n1 over to xnn. So if we multiply this matrix by this column matrix, we get this thing, which we can then separate into this. So all of these are equivalent ways of writing this solution. The point of this was to get to this matrix phi of t. Phi of t is called the fundamental matrix of the system. Fundamental matrix because it is formed by the fundamental set of solutions. Each column is one of these columns. So that's our fundamental matrix. Two important facts about the fundamental matrix that we will make use of. Phi of t is non-singular. That means it has an inverse. That is important because we need the inverse of that matrix. So this is a non-singular matrix. How do we know? Well, if we look back at phi of t, the determinant of this matrix is the Wronskian of that system. And we know for a fundamental set of solutions, the Wronskian is not 0 for all t in our interval of solution. So this matrix has an inverse. And the second important fact is that phi prime of t is a times phi of t. Because phi is made up of all of these solutions to our equation. So we take the derivative of this matrix, we just get the derivatives of all of these solutions. So we get the derivatives, well, that equals a times the solutions themselves. All right. So that's our setup for variation parameters. We need that phi of t matrix. So here's our method. So we want to replace our constants times our functions here. We want to replace these constants by some unknown functions. That's what we did in our original method. We said, well, is our particular solution made up of some function times our known solution for the homogeneous equation. We're going to do the same thing. we're going to say u of t is a column matrix of some functions, u1 of t, u2 of t, to un of t. And we want our particular solution to be phi of t, which contains our known solutions, times u of t. And we want that to be a solution of x prime equals ax plus f of t to our non-homogeneous equation. Well, if we take the derivative of this thing, x prime of p, using the product rule, and remember we're dealing with matrix quantities here, so the order of the multiplication is important. We need to keep the order phi of t and u of t the same. So this is going to be phi of t u prime of t plus phi prime of t times u of t. And we're going to substitute xp, x of p, and x prime of p in the original system. So we're going to substitute that in here. So I'm going to switch pages here. I want to make sure we're all clear on what we're doing. So we're substituting this into our original system. We're going to do some work with that to try to somehow get to something that we can solve then for u of t. Exactly like we did with variation of parameters before. So we get phi of t, u prime of t, plus phi prime of t, u of t, equals a times phi of t, u of t, plus f of t. Well, we said before that phi prime of t times u of t is a times phi of t. That was one of the properties of the fundamental matrix. So we can write phi of t, u prime of t, plus a phi of t equals a phi of t, u of t, plus f of t. Oops, I missed a, yeah, this just phi prime is a, so I need a u of t here. I put my brackets too big. Well, we have this quantity on both sides of the equation that we can subtract. So we get phi of t, u prime of t, equals f of t. Very similar to when we did variation parameters before. We had something like this, and we divided by this quantity to get u prime, and then we integrated that something divided by the other thing. Well, here we can't divide because phi of t is a matrix. So what we're going to do is multiply both sides by phi inverse. That's kind of the analog of division in the world of matrices. We multiply by the inverse. We get u prime of t equals phi inverse of t times f of t. And I need to multiply here on the left, because I'm multiplying on the left-hand side, phi inverse times phi gives us the identity matrix. And then u of t is the integral of this thing. So that's going to be the integral of phi inverse of t times f of t dt. And we evaluate that integral by integrating each component of the matrix, column matrix that we get when we do this multiplication, column vector. So this gives us a way to solve for u of t. That's the column matrix of those functions that we were looking for. And our general solution then x equals phi of t times c. This is our x of c, our complementary solution, plus phi of t, because we need to multiply this by our original matrix here to get our particular solution. Phi of t times the integral of phi inverse of t f of t dt. Very similar to what we did for variation of parameters with higher order differential equations. Exactly analogous, because our integral was f of t divided by, we had something divided by some other function times our original function. And this thing that we had in here had to do with the Wronskian of our system. So phi of t sort of has to do with the Wronskian. It's just the matrix of those functions that make up the Wronskian. Yes?
Wait, the c on like the x of c, or that's just like c1, c2?
Yeah, that's this solution that we get for our homogeneous equation. All right, so questions on our setup here. So I want to go through an example. The basic procedure is we find our complementary solution, use those functions to form our phi of t, and then we find phi inverse, multiply it by our f of t, those functions that make our system non-homogeneous, integrate that, and then multiply that again by phi of t. And I'm going to go back here. Our constants, we don't need to worry about the constants of integration, just like we didn't need to worry about the constants of integration with our variation of parameters with higher order differential equations, because the constants of integration can get incorporated into the constants of our original solution. And a reminder, if matrix A is A, B, C, D, A inverse is 1 over the determinant of A times, we switch these two, change the sign on these two. I'm not going to have you find inverses of 3 by 3s. we would use technology to do that. The process for finding the inverse of 3 by 3 is a little more involved, but 2 by 2 is very easy to find the inverse. All right. So here's our system. X prime.
Is C negative or is it?
Oh, did I forget to change the sign? Yes. 1, 8, 1, negative 1. X plus e to the minus t, t e to the t. And we're going to use undetermined coefficients. So our first step, we need to find our complementary solution. So to do that, we're going to solve determinant a minus lambda I equals 0. So we get 1 minus lambda, 8, 1, negative 1 minus lambda. That determinant is 0. We do some work here, and this gives us lambda squared minus 9 equals 0. So lambda equals plus or minus 3. For lambda equals 3, we need to find our eigenvectors now. I get negative 2 k1 plus 8 k2 equals 0, and k1 minus 4 k2 equals 0. So from this one, we get k1 equals 4 k2. And I let k2 equal 1, so k1 equals 4. And our first eigenvector, k1, is 4, 1. For lambda equals negative 3. After a while, you do so many of these, it's just this process is almost like clockwork. You're just like, okay, cranking out these eigenvectors. We get 4 k1 plus 8 k2 equals 0, and k1 plus 2 k2 equals 0. So k1 equals negative 2 k2. I let k2 equal 1. So k1 equals negative 2. So our second eigenvector is negative 2, 1. And our complementary solution, x sub c, is c1 times 4, 1 e to the 3t plus c2 negative 2, 1 e to the negative 3t. And I'm going to form my fundamental matrix from these solutions. So phi of t, I just take the first column is the eigenvector times this function. So we get 4 e to the 3t, 1 e to the 3t. Don't need to put the 1 there. The second column is the eigenvector times this solution. Negative 2 e to the negative 3t, e to the negative 3t. That's our fundamental matrix. We need the determinant to find the inverse. So the determinant, phi of t, is 4 e to the 3t times e to the minus 3t, which is 4, minus negative 2 e to the negative 3t, e to the 3t, so that's plus 2, which is 6. Our determinant is not always a constant. It could be a function as well. So phi inverse of t is 1/6. I'm going to switch these two. E to the negative 3t, 4 e to the 3t. Change the sign on these two. I'm going to rewrite that as 1/6 e to the negative 3t, 1/3 e to the negative 3t, minus 1/6 e to the 3t, and 2/3 e to the 3t. That's our inverse matrix there. And then I'm going to switch pages here. So we're going to multiply this by f of t. There's f of t. F of t to get u prime. So u prime of t equals phi inverse of t times f of t, which is 1/6 e to the negative 3t, 1/3 e to the negative 3t, minus 1/6 e to the 3t, 2/3 e to the 3t, times e to the negative t, t e to the t. And I'm going to write this out explicitly, my multiplication. So u prime is first row times first column. So I get I get 1/6 e to the negative 3t times e to the negative t plus 1/3 e to the negative 3t times t e to the t. And then my second row is going to be negative 1/6 e to the 3t times e to the negative t plus 2/3 e to the 3t times t e to the t. And I multiply and simplify, and I get 1/6 e to the negative 4t plus 1/3 t e to the negative 2t, and I get negative 1/6 e to the 2t plus 2/3 t e to the 4t. So that's u prime. I'm going to integrate that to get u. U of t is, I'm going to write this the way we wrote it in our formula, is the integral of phi inverse of t times f of t dt, which in this case is going to be the integral of this matrix. dt, and I'm just going to integrate each row. First components here, that's a u sub. Second components, that's integration by parts. So not super difficult integrals. These you have to keep track of the constants a little bit here. So when we integrate, finally, I get, well, I'm not quite finally yet. U of t is negative 1/24 e to the negative 4t minus 1/6 t e to the negative 2t minus 1/12 e to the negative 2t for my first row. For my second row, I get negative 1/12 e to the 2t plus 1/6 t e to the 4t minus 1/21 e to the 4t. Almost to our particular solution now. We have our functions that we need to multiply by the solutions to our homogeneous equations, yeah. So we get x of p is phi of t. Those are our original solutions to the homogeneous equation, times u of t. So that is the matrix for e to the 3t negative 2 e to the minus 3t, e to the 3t, e to the negative 3t, that's phi of t, times this thing. And sometimes with this method, the most difficult thing is just writing everything out, not actually doing the math. All right, so now we need to multiply this 2 by 2 matrix and this 2 by 1 matrix. So I'm going to write out explicitly what that multiplication is. So we get 4e to the 3t times all of this.
Is this a point where it'd be okay to use a computer?
To do this multiplication?
It looks harder than it is.
It's just it's more writing than anything else. This times this plus this times this. So we get minus 2e to the minus 3t times this. That's the first row. That's one row. And then we have the second row. So we get this row by these two. So that's going to be e to the 3t minus 1 24th e to the minus 4t minus 1/6 t e to the minus 2t minus 1/12 e to the minus 2t plus e to the minus 3t times this. And then we multiply everything out, combine like terms, simplify a little bit, and this becomes negative t e to the t minus 1/4 e to the t for my first row, minus 1/8 e to the minus t minus 1/8 e to the t. See, that's not that bad. And finally, the general solution, x is c1, 4(1) e to the 3t, plus c2, negative 2(1) e to the negative 3t. And I factored out a negative, so I said minus t e to the t plus e to the t 1/8 e to the minus t plus 1/8 e to the t. And there is our general solution. Then I wrote it all out. Just so you believe me.
It's like that you only have one exercise.
Um,
Yeah, but yes, yeah.
Well, it's probably easier on the.
What about this?
I think you're missing a 1/4 on you're lowering the.
Oh yeah, this should be a 1/4 here.
All that work. So you can't
I think
stop
that
that
should
long.
be done.
See, that's the problem, is you do all that work and then you make a
I wouldn't take anything off if you just forgot that 1/4. What about this?
I like it.
What? I would say hugging the ball or something.
Oh shoot.
That's 1/4 push T. So I would say that variation of parameters, generally not particularly difficult. I mean, the integrals, depending on the functions, the integration can be difficult. Really, honestly, there's just a lot of stuff to write because we're dealing with all matrix quantities. It's just a lot of volume of stuff.
Yeah, I'm gonna use a computer not because I can't do it, because that just is like a lot of time.
Yeah. I'm not sure I believe you though.
You don't think so?
I'm not sure. You have to you have to prove to me that you can do it. Yes.
There was part of the solution. Can you put in like the I of T, C, and like the C matrix one, where it was just like I of T times.
Oh yeah, yeah. So if you wanted to write it like, are you saying can we write it like this? Yeah. That's an acceptable way to write it. I just wrote it the other way because that's generally how we've been writing.
Wait, what is that I looking thing called again?
Phi.
Phi.
It's capital Phi. It's like our
Yeah.
phi from spherical coordinates. It's just the capital of that letter.
I just like forgot for a
Yeah,
second.
me too.
You just kept saying
As soon as I compete, because I forget it.
All right, questions on variation of parameters. And I will say the homework is not, generally this is worse than any of the homework problems. The homework problems are not too bad. They're really not too bad. When I worked through the solutions, I went through most of them for me, writing in a lot of detail in about 30 minutes.
I thought that was gonna be
We have
like
to do
a
this with, like, the
1,000
complex
Like I did the test in
Yes.
minutes, guys.
So those would just appear here in the complementary solution. No, I did most of the homework the homework assignment in 30 minutes. So it's not, this is worse than any of the problems in the homework.
Like this took me 6 minutes.
Yeah,
I'm
the
doing
writing,
one period.
the writing just to write down what you need
Like-
takes more than 6 minutes. You are.
Well, in all fairness, she doesn't teach it. She teaches it twice every day.
I mean,
done this for 20 years.
If you look at her lecture notes, she writes so quick. I mean, I believe.
I always had her on double speed.
Yeah, and
Yeah,
it's
you
just
only watch
words
one.
are being filled in instantly in double speed.
Watch her take one.
There we go.